welcome to STEMtastic 21. We are delighted to be joined by the team at ESCOL Lab, the Physics Education Research Facility at CERN, home of the Large Hadron Collider, and the European Organization for Nuclear Research in Geneva, Switzerland. Very warm welcome to Dr. Sarah and Dr. Anya. They are going to be presenting It's Just a Phase, so I will hand over to them in just a moment. Before I do, to say that your microphones will be on mute. The presenters can't see you. If you would like to ask a question, I apologize. If you'd like to ask a question, please pop it in the Q&A box at the bottom. Over to you, Sarah and Anya.
Yes, hello. Thank you very much for this short introduction. It's 3 minutes to 1, but I guess then we are good to go already.
Yes, you're great to go.
Okay, thank you very much for the feedback. Good. Okay, then good afternoon, dear audience, and welcome to CERN, the European Laboratory for Particle Physics in Geneva, Switzerland. Here at CERN, we explore the structure of particles that make up everything around us. We do so using the world's largest and most complex scientific instruments. My name is Sarah, and I will be your guide today. Right now, I am sitting in the control room of our student laboratory called School Lab. And I want to introduce you to what my work looks like. And there is no better way than for you to join me at my workplace for a bit. So in order for this to work, I will need your help. In this control room, we often get calls from various researchers that have problems with their equipment, and we are the ones to help them fix their problem. Today, I need you to be my new co-workers and help me help our researchers. So every time I will need your help, I will launch a poll, and I would like you to try and answer as quickly as you can. So let's try one of those polls for the start. I will launch it. Are you ready to start the science show? Yes, I want to start now. Or well, can we wait 10 seconds? Or OMG, yes. 4 out of 11 have already voted. We will wait for some more. So click on the answer you prefer, and then we will see what to do next. So you've got a minute. And in the meanwhile, I will make myself some coffee. So if you hear some water boiling, okay. My water for the coffee is ready, and in the meanwhile, everyone has answers. Okay, so let's check. And I will end the poll and share the results with you. So yes, you are ready to start, then let's go ahead. Perfect. If you have any questions, you can post them in the question and answers, and I will answer them in the end. Okay, so before we can start, I would like to show you how our office looks like.
Hello.
So this.
Hello, CERN control room. Are you there?
Good afternoon. How can I help you?
Oh, I'm so happy you answered. I think my detector is broken, and I don't know what I can do to make it work.
Okay, wait. Which CERN's detector do you work for? I'm not sure we have met before.
Oh yeah. Sorry. Where are my manners? That was super rude of me. So I'm Anya, and I'm a student. I don't yet work at CERN, but I really want to. But yesterday I watched a documentary on CERN, and now I want to do some of the experiments that CERN does, but like in my room. So I wanted to make my own particle detector. I Googled how to make a particle detector, and I find a so-called cloud chamber, but now it just says error, and I don't know what could go wrong. Oh, I thought you could surely help me. You work at CERN.
Ah, okay, no problem. You're lucky. Today I have a group of helpers that will make sure that we can fix your problem as soon as possible. Too bad it doesn't say what kind of error it is. What could that be? Okay, so you said that it is a cloud chamber, right? And most often cloud chambers have problems with phases.
Phases? Like when my mom says that my love of Shawn Mendes, is just a phase?
No, not that kind of phase. When I say something in your detector is not in the right phase, I mean that it's not in the right phase of matter. One can also call it state of matter.
I still don't get it.
Okay, well, let's look at water. As you know, I've just boiled some water for the coffee, and I have a little poster about water that I will share with you. Great. So water has 3 phases of matter. At room temperature, water is usually a liquid. It flows, we can't really hold it, and it makes droplets. If we cool it down enough, it will freeze.
So like turn to ice, right?
Yes, at temperatures below about 0 degrees Celsius, ice or frozen water is solid. So we can easily hold it. But if we would instead heat the water up, it would eventually turn into gaseous water or water vapor.
Is that what happens when the water is boiling? I was always wondering, where does it disappear if I leave it boiling? It just goes, it's not there.
Yes, it looks like it has disappeared because usually we cannot see gases. That's also why there is no picture of gaseous water on my poster. When liquid water becomes gaseous, it looks like it disappears, but actually it only mixes with the air around us.
So does that mean that there is water vapor in the air?
Indeed.
Oh, nice. Oh, cool. Okay, so maybe in the detector, something that is now visible, like when we have liquid water, should be made invisible. I mean, in order for it to work. Does that make sense? Should I put the detector in the water heater and boil it? Okay, it doesn't fit like this because it's pretty big, but maybe if I take my hammer, where should
I would not do that if I were you. If you break your detector with the hammer, then it will certainly never work again. Maybe we can try something else.
That is a very good point, but I always use water heater for boiling water.
Well, just because something is always done in a certain way doesn't mean that's the best way to do it. Wait, let me show you something. I will take a syringe, like this one. Then I will close the opening with my finger, like this. Before that, I will put some water in the syringe, so water that is hot, but not boiling. Okay, so then the finger on top. So that air doesn't go out, and then I will pull on the plunger.
Okay.
What do you think will happen with the water?
I have no idea. Isn't it something that your co-workers could know?
That's a great idea. So, dear co-workers, I have a question for you. What do you think will happen? I will launch the poll. Yes, so what do you think will happen when we pull the plunger? Will the water inside the syringe freeze? Will the water inside the syringe boil? Will air bubbles enter the syringe? Or will nothing happen? Let me get ready in the meanwhile. So I have a glass here, and I will just use the water that I've boiled for the coffee. I am pouring. And I want to point out, as you can see here, the water is, yeah, it's warm, but not boiling.
Yeah, not boiling at all.
Great. So I will take some of the water. Good. So I have put some hot water inside and I leave a tiny bubble of air. Usually we don't want this bubble, but for this experiment it's important. So I close the opening so that the air doesn't go out. Anya, can you read exactly how much water and air is in the syringe?
I can't see how much air, but together it's about 15 milliliters, if I see correctly.
Yes, exactly, 50 milliliters. And in the meanwhile, most of my co-workers have already answered.
What did they say?
I will share the result with you. So my co-workers think that nothing will happen.
That is a possibility. Could be. I don't know. Can you show? Can you show?
Yes, I will. Okay. Now we have 15 milliliters of water and air. And now watch carefully what happens when I pull the plunger. So are we ready?
Yes.
3, 2, 1, go.
Oh, wow, it's boiling.
Yay! Can you see that?
Awesome, it's actually boiling. But maybe it's air coming in, but it looks like it's boiling. It's like, you know, when you have water on the stove and it starts boiling and it's bubbles and...
I will show once more.
No.
Okay, and now let's check what happens if I let the plunger go again, go back to its initial position.
Okay.
So I will now check how much of air and water we have. It's still, wait a bit. Oh, it's still 15 milliliters. Can you see that?
Yeah, it looks exactly this. So that means that air didn't come in. It was actually boiling.
Exactly. So we can be pretty sure that the water was really boiling and that there was no air coming inside. What happened is that because the air bubble expanded, the pressure dropped. And that made the water boil at a lower temperature.
That's awesome. So you're saying that you can make things boil by changing either the temperature or pressure. Awesome. That sounds awesome.
Yes, you can also change both at the same time. For instance, if you go on top of a very high mountain, you need to heat up water for less to get it boiling. On Mount Everest, it boils so quickly that you cannot even cook an egg.
What? That's crazy. But Sarah, how does that help my experiment? It's not like I'm checking for eggs.
Oh, yeah, true. Actually, good point. Thank you. So your detector, we could try to change the phase either by changing the temperature or the pressure. But as we don't know for sure what kind of error it is, we are just guessing. I almost forgot. My co-workers can help me with this guess. So I will launch another poll. Dear co-workers, would you like to fix the detector by changing the pressure or by changing the temperature? So changing the pressure means that we would squeeze something, and changing the temperature means that we would freeze something.
Wait, freeze something? Oh, I would love to freeze. Can we freeze something? We haven't had like a super cold winter here, so I kind of miss cold. So I would really like to freeze something. Can we make ice? Can we make ice cream? But the experiment that we just did was also super cool. So maybe we should start. Can we make ice cream with pressure? Maybe not. But like the pressure changes were really cool. But freezing, I really want ice cream. Decisions. I don't know what I would.
Don't worry, my co-workers got you covered. They chose instead of us.
Okay.
And let's check what they decided on. So they say we should try it with changing the temperature.
Freezing. Just what I wanted. So, okay. Freezing. What should we do?
Okay. First, you need a very cold liquid. Do you have anything super cold close to you?
If it's cold, I better put my winter gloves on. And let's check. Yeah, I have something. It says it's super cool. You see it?
Yes, it even says it in German.
Yeah, it has some warning signs of it. I guess this is it.
Yes, it is. Perfect. It says Stickstoff, which is German for liquid nitrogen. Nitrogen turns into liquid at minus 196 degrees Celsius, so you better not touch it.
But how do I know it's really cold then?
Well, do you have a thermometer?
Nah, I have a banana. Banana kind of looks like a thermometer, or maybe an orange. And I have a broken detector, but that one, I don't think it, no, it doesn't fit.
Neither of those can tell us exactly how cold it is, but we could use the banana or the orange to check what would happen to your finger if you would put it in the liquid.
Okay, but this container looks really clean, and I can't put my hand in it, I can't clean it, so let me put it in something else anyway.
Do you maybe have a double wall cylinder out of glass?
Okay, yeah, I do. Let me bring it here. Look at it, it's so pretty. It's for my daily doses of tea, because I drink a lot of tea and I need a big glass. So I have this. And now I put liquid nitrogen, right?
Yes, please.
Whoa! Sarah, didn't you say this is cold? This isn't cold, this is boiling. Oh my God. It boils even more than in syringe. Can you see that?
Yes, I see it. Well, if it's boiling, you shouldn't touch it anyway. But actually, the nitrogen that is in the cylinder would usually be in a gaseous state. To make it into a liquid, it had to be cooled down to those minus 196 degrees Celsius. As you put that cold liquid to room temperature, it starts boiling to go into the state it would usually be in at room temperature, namely gaseous state.
So you're now saying that this is boiling at minus 196 degrees Celsius? That's crazy.
Yes, well, at the normal pressure in your room, of course. Changing the pressure would again change the boiling temperature. But just to make sure that it really is super cold, use a piece of either banana or orange to try it out yourself. Which one will you pick?
I'm not sure. So banana kind of looks like my finger, but bigger. But I'm orange because I have orange hair, so maybe orange is a better. I don't know. Can your coworkers pick?
Well, actually, that's a good idea. I will launch another poll and we will let my coworkers pick. What should we put in the liquid nitrogen, the banana or the orange?
But Sarah, why would any of these two be a good representation of my finger? I mean, yes, this one looks like my finger, this one looks like my hair, but my fingers are not made out of fruits. At least not the last time I checked.
That's true, but both your finger and fruits have a lot of water hidden inside. If that water freezes, it can damage the cells and everything becomes, well, let's see what happens. My co-workers have chosen the banana.
Banana. Yeah, of course, because it looks like my finger, right? Yeah, okay. Then I will take this chopping board. I will open the banana.
Great. You take one piece.
Yes. Good enough? Yeah.
Looks great.
The liquid nitrogen. There's not enough. Let me check if I can put some more liquid nitrogen to freeze the banana. Are we gonna make ice cream?
Banana sorbet. That looks good. Wow, you have a crocodile.
Yeah, it helps me with cooking. See? Perfect for making banana ice cream. This is boiling really hard, and you can see like you have so much smoke. Is this smoke?
No, that's not smoke. So what you see coming out of the liquid nitrogen is actually, not smoke, it is fog. As the liquid nitrogen boils, it turns into gaseous nitrogen, as we've already discussed earlier. Mm-hmm. But that gaseous nitrogen is still very, very cold. It's so cold that the water vapor in air that we talked about before turns back into liquid water. So what you're seeing is water droplets, the same as when there's a cloud in the sky or fog outside your door.
Oh, okay, so that's the same reason. I mean, during the night, it also gets colder. So in the morning, I see fog outside because the water vapor cools down, right?
Exactly, and by that turns into liquid. So when the air outside cools down, the water vapor in the air turns into millions and billions of tiny water droplets. And those droplets interact with light, and that is what we see as fog or cloud.
Nice. So when cooling down gases, they turn into liquid. And when cooling down the banana, it will turn into ice cream?
I think it's time to take out the banana and try it. Okay. Put it on the table and smash it with the hammer.
Okay, banana is here. Oh, it broke already. What? Bananas don't break. Like, but this one does. Have you seen this? Look, 3, 2, 1. That's gonna leave a mess. Oh my God, that's so cool. It's like glass.
Exactly, wow. And that's what could also happen to your finger if you held it inside the liquid nitrogen for too long. The water inside would freeze and your finger would, well, break.
Ouch. Well, I would like to see my fingers as glass, but maybe not that much. Maybe it's better if I don't try it, huh? But okay, I now know that this is really cold. Should I just pour it over my detector?
Well, your detector is not made of the same material as your finger or your banana.
So it should be safe, right?
But it is filled with gas. And when gas cools down,
it turns into a liquid. Yeah, we talked about that.
Well, yes. And in the process of cooling down, well, I think it's best if you make another experiment. Do you have a balloon?
Wait, I have to go and get it.
That was fast.
It have to be like this, like a regular balloon?
Yes, that's actually a really nice balloon. So please pump it up.
Yeah. Oh, I get it. It's because we need to put some air in it, right?
Yes, exactly. Usually we forget about the air and that it exists at all, but air surrounds us all the time. And if we want the balloon to be blown up, we also need some air inside.
Yeah.
Some more air.
Okay, so when I pump it up, do I put it in the liquid nitrogen?
Yes, so what do you think will happen when you put the balloon inside the liquid nitrogen?
It will freeze, like the banana. I mean, because this is still solid, so it will freeze and break.
Well, let's ask my co-workers what they think. I have another poll for them. When we put the balloon in the liquid nitrogen, will it shrink, pop, expand, or change its color?
Changing color would be so cool. Imagine putting this one that is blue and then it would turn into a red one. Oh, that would be so cool. But I still think it will freeze, and then because it will freeze, it will pop. But if it pops, it also shrinks, right?
That is true, but does it need to pop in order to shrink?
Yeah, I mean, I never saw it shrink for a different reason.
Just because you've never seen it happen?
That doesn't mean it's, yeah, it's not true. Yeah, I know. I got it from the previous experiment. Yeah, I got it. But I don't know.
Okay. Yeah, let's check maybe what my coworkers think. I will end the poll and share the results with you. So they think it will pop. Oh, so they agree on your suggestion. I think it's best if we go ahead and try it out.
Okay. So I will take this liquid nitrogen that I still have in front of me, and I will put the balloon inside. 3, 2, 1.
Great.
Is anything happening? Oh wow. It is shrinking.
It is.
It's no balloon. It's like the empty balloon now.
Yes, it is becoming smaller and smaller, but
Must have popped.
did you hear it pop?
I mean, no, but maybe it was like a silent pop or like a silent fart or something.
Well, if there was a pop, there has to be a hole somewhere as well. Wow, it's even becoming smaller. Really nice. Yeah. Well, take out the balloon and check for any holes. Then we know if it was popped or not.
Yeah, I can't check it inside. I will have to take it out. It's cold, so I will use my crocodile. It became naughty. Okay. But, oh my. It's becoming bigger again, and it has turned into 90 degrees balloon. But
wow.
A popped balloon never goes back. Like, how did that, I mean, like, I don't know what happened.
Okay. So, as we've already mentioned, inside the balloon is air. Obviously, the balloon did not pop, but so we still have the air inside, and air is made out of tiny, 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 tiny atoms, and that move around all the time. And when it's hot, they move around a lot and take a lot of space.
Okay, so when they're hot, they move around a lot. It's like me in the summer, because when it gets hotter, I like to go running, I like to go hiking, but I don't like to go hiking and running when it's cold. I rather stay on the couch.
Yes, and same happens with the atoms. I will share something with you where we can observe better what happens with the atoms. Yeah. So here you can see that When it's cold, the atoms don't move much. So if I switch to degrees Celsius, we have a low temperature here. But and that's what was the case when the balloon was in the liquid nitrogen. And now I will heat up. So we take the balloon out and look what happens with the atoms. So,
oh wow, they're moving more and more.
Yes, they're moving more and more. When it got warm again, the atoms started moving more and more, and the balloon inflated.
Nice. Awesome. But Sarah, how could that help me with the detector? What should I do?
Well, it could help you, but be careful. Only pour a little bit of liquid nitrogen on the side so that only the lower part cools, while the gas doesn't shrink too quickly. That could damage the detector.
Okay, so I don't need the balloon. Okay.
No, we don't need the balloon. We need the liquid nitrogen.
Okay, I will take this one. On the side, right?
Exactly. Pour a bit on the side so that only the lower parts cool down.
Careful, careful, careful. Nothing. I can still see an error and it does nothing. Should I put some, let me put some more. I can hear something, but nothing happens. Still shows error. Oh, this was a mistake. Do you have any other ideas what we could do?
I'm thinking. So we already know that your detector is a cloud chamber,
yes.
Correct?
Yes.
Maybe we should make a cloud.
Like we just did, the one that comes from the liquid nitrogen, right?
That would have worked now already.
Yes.
I mean an alcohol cloud.
An alcohol cloud? How is that even allowed? How do you do that?
Let's demonstrate it with an experiment. So you don't want to test it directly with your detector, just in case.
Okay.
So please take a bottle, a cap for the bottle with a hole in it.
Bottle,
great. Cap with hole. Amazing. Then we need some pasta dough or Play-Doh.
I don't know how to make pasta dough, but I do have Play-Doh.
Great. And a spray duster. That's like a bottle with gas under high pressure. And we use it, for example, for cleaning keyboards.
Yeah, I have that because I was cleaning my stuff. Here. Yeah, this looks like it. It has a keyboard, so yeah, probably that. Oh, and don't we need like alcohol for an alcohol cloud?
Yes, of course. You need some isopropanol, like the one we use for disinfection.
See, I'm smart as well. Alcohol.
Never doubted that.
Isopropanol.
So pour the alcohol in the bottle and close the bottle.
Alcohol is this thing? The whole thing?
No, just a little bit.
Just a bit, okay.
Then you roll it around so that the walls are covered with the alcohol.
Why do I need to disinfect the bottle?
Well, that's not for disinfection. By doing this, you make sure that more alcohol goes from liquid to gaseous phase. And you know it's turning into gas because you can smell it, which means that the alcohol is reaching your nose.
Yeah. Oh. I should not have done. Advice to anyone: don't smell alcohol. Oh, this is I feel like my nose burns a bit.
Yeah, alcohol smells really bad. But gaseous isopropanol will be very important for our experiment. Okay, so next you put the spray duster through the hole in the cap and secure the opening with Play-Doh.
Okay. Spray duster through the hole in the cap.
Okay, now wait a bit, let's make a hypothesis.
Okay.
What you will do next is you will spray some gas into the bottle. Then you will quickly take the spray duster out. This means that you are opening the bottle, and the question is, and I will pose this question to my colleagues, to my co-workers. So when Anja opens the bottle, will a cloud appear inside the bottle, outside the bottle, both inside and outside the bottle, or will nothing happen?
You already asked before if nothing will happen and then something happened. I don't think you are doing the same thing again. So maybe nothing will happen, but then again, you said that there will be a cloud. So I suppose that there will be a cloud, because otherwise, why would you say it? I don't know.
You never know. Maybe I have fooled you.
Maybe you did. But why would there be a cloud at all?
That is a very good question. When you spray gas inside the bottle, you are increasing the pressure as you are squeezing more and more gas in the same volume. And once you open the bottle, the gas from inside can quickly expand. The pressure drops, and well, my co-workers think, I will share with you, that a cloud will appear inside the bottle. But let's try it out.
It will happen. I don't believe them at all. I think there will be no cloud. I think you fooled us.
Well, then let's try it out.
Okay, so I have to put some air inside the bottle, right?
Exactly. And then you remove the cap.
I just open the cap normally, or? Okay.
Yes.
Okay, here we go. Let's count to 21 because it's 2021. 1, 2, 3, 4, 5. 18, 19, 20, 21. Okay. And now we open the cap. Whoa! There is a cloud inside the bottle. There was a bit outside as well, but inside is the biggest one. Nice. Can you see how it's flowing from one side to the other if I do it like this?
Yes, it looks really cool.
Oh, this is really cool. This looks like magic.
It's actually way cooler than magic. It's science. See, when the gas expanded, the pressure dropped, and all the gas from inside the bottle, including the alcohol vapor, cooled down by a lot. You can feel this if you touch the sides of the bottle now.
Oh, yes. Oh, they're really cold.
Yes, and due to the change of pressure and temperature, the alcohol turned from gas to liquid, the same way water vapor did before with the fog around the liquid nitrogen.
Amazing. I guess I should do the same thing with my detector now. Spray some gas, put some Play-Doh, and try to make a cloud.
Indeed, try if that works.
Okay, detector. There we go. No, some alcohol, right? Alcohol inside the chain. Da, 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 da. Okay. Now we put this next to here, secure it well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Nope, that was just me. Nope, nothing happened. We will never make this work. We're just guessing here.
Ah, don't give up just yet. We still got some phases and phase transitions to try out. One of them ought to work.
Okay, other phases. So you mean this was gas and so solids, right?
Nope.
Liquid?
Nope.
Ah, okay, gases. But we just did gases and it didn't work.
It's not gases either.
How do you mean it's not gases either? I said solids, liquid, gases, that there's 3 phases of matter. I mean, what else could there be?
Well, there are more phases of matter than that, and
No.
yes, and the amount of phases depends on whom you ask. There might be many more. But in a cloud chamber like yours, that is a bit more advanced from the looks of it, we usually need 5 phases. We need gas and liquids to make a cloud. And we need solids around to hold the detector together. And then, in the end, we need 2 more phases to make the visual detection part work. We need plasma lightning to make the detection visible, and superconductors to bring electric energy to the light itself. And as we tried everything else, it's one of the 2 that is the problem. Again, we need to guess which one it is. Let me ask my coworkers, with which state or phase of matter would you like to fix the detector? Either with plasma lightning or with superconductivity.
These 2 both sound cool, but I have first a different question. If there are more than 3 phases of matter, does this mean that my physics teacher lied to me?
No, he just did what scientists have to do quite often. He simplified. Solid, liquid, and gas are the 3 states of matter we deal with the most in our daily lives. Therefore, knowing those 3 is the most useful.
Okay. Well, then I would like to see plasma lightning because that sounds cool. Although superconductors sound quite cool as well.
Luckily, it is not up to you. Let's see what my co-workers said. I will share the results.
Plasma.
They chose plasma lightning.
I would have picked that one as well. Plasma sounds awesome. Okay.
Yes. So sure you would have picked that one.
But Sarah, what is plasma anyway? Is this just like plastic? Because like, yeah, on top of this is plastic. Is this plasma?
No. It's way more fun than that. Plasma is a state of matter at which the atoms in the matter move so quickly that they actually lose some of their electrons.
You mean electrons as in part of themselves? Like, I mean, atoms are made out of the nucleus and the electrons. So it's like if I would run so fast that my arms would fall off.
Exactly. Atoms lose a small part of themselves because of their rapid movement in plasma state.
Imagine that, me running and my hands falling off. Okay. So if we return to what was what we talked about before, if atoms are moving super fast, that means that plasma is probably super hot, right?
Yes and no. One way of achieving plasma is by increasing the temperature.
Okay.
One such example are stars. Stars are basically super hot plasma balls.
Plasma. Oh my god, this is amazing. I have a plasma ball. Is this a star?
No, this is not a star. Plasma balls use a different principle. They use electricity. Basically, what plasma balls do is similar to the second example in nature, lightnings. Lightning is also a streak of plasma. Go ahead, try it, turn it on, and let's try it out.
Okay, if it's lightning, maybe I should turn other lightning down first.
Yes, and then we can observe what you see. Well done.
Yes. Okay, see what we get. 3, 2, 1. Whoa. Oh, look at this. Oh my gosh. Can you see this? Can I touch it? 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 Can I touch it?
Yes, you don't need to worry. Although it is always wise to be careful around electrical devices, this one is harmless. You can freely touch it.
3, 2, 1. Oh, look at that, look at that, look at that, look at that. The lightning goes directly to my finger. Oh my God. Oh, look, it goes from one finger to another. Oh my God. I am like Zeus, the god of lightning.
Or a student that learned something. That's actually same. But Anya, if you want to fix the detector, you should probably stop playing with the plasma ball.
Wait, sorry, detector, we wanted to fix the detector, but what should I do? Lightning, stars are lightning, and they are on top of us, so detector, I put it on top of the detector, right? Like a star.
Well, you can try it.
Ta-da! Nope. It doesn't work.
That's because the cloud chamber works best with a linear light source.
Linear light source? What is that?
Yeah, you know, like a light tube.
Oh, you mean like fluorescent light tube? Like this one?
Exactly, that's perfect. Where did you find this?
Oh, this one is a replacement for the one we have in our kitchen, but you can also find this like in different schools and hospitals. And I saw in the documentary on CERN that they have something like this in their laboratories.
Indeed, so most fluorescent tubes use plasma to produce light. And I believe yours is perfect for solving your problem with the detector.
Okay, finally. I hope this works. I hope this works. But what do I do?
You take the fluorescent tube and put it closer to the plasma ball.
Okay, plasma ball, fluorescent tube. Wow, this glows. Oh, look at it. Look at this. If I move it, it glows more and more and more and more. And then it goes. Let's go to the other side. Let's go to the other side. Let's go to the other side. Yes! Sorry. This is awesome.
Yes, so the electrical effects from the plasma ball continue beyond the ball and are able to create a glowing plasma inside the fluorescent tube as well.
Left. Oh, this is so cool. So I can use this to make my cloud chamber work, right?
Let's try it. Bring the plasma ball closer to the detector and then use the fluorescent tube to illuminate the bottom part of the detector.
Okay. Three, two, one. Nope, I lost it. Let's do it again. Two. Nice. It works.
Wow.
It works, and I can see stuff inside. Oh my God, this is so cool. Thank you so much. Oh my God. Do you want to see it? Do you want to see it? Do you see it on the camera?
I don't see your camera yet, so maybe you can share what you see in the camera.
Oh yeah, yeah. On the actual camera of the detector. Let me share the program. So I will share my program with you. Can you see it? There's like stuff moving inside.
Oh yes, I can see it.
Oh no, the camera is down. The camera is down. Okay, it's back up. Yeah, I shouldn't have followed just the first example on the internet. This camera.
But now I see it. It's moving lines.
Nice. Yeah, live, it's even better. You have to do it at home. It's awesome. Thank you so much. This is so cool. But actually, I don't know what I see. I just see like it's just like tiny clouds moving around, but I don't even know what this is.
So yeah, actually that's a good question. And luckily I can also explain you what you can see. Look, I have another poster for you.
Okay, sure.
So in the cloud chamber, you can find gaseous alcohol everywhere in the cloud chamber.
So we can make the alcohol cloud, right?
Exactly. So like we had in the bottle before, again, you cannot see the gaseous alcohol.
Mhm.
That's why next to the gaseous alcohol, there's a red cross because we cannot see it. Again, however, the cloud chamber is super cold at the bottom. There is dry ice that's like minus 80 degrees, super cold.
Mhm.
And the gaseous alcohol below this dry ice cools down and do you have any clue?
I know it. It makes a cloud like it did before in the bottle.
Exactly. Can you see how there are additional cloudy lines appearing in this alcoholic cloud?
Yes. What are those?
Yes, I will explain in a bit. So I want to point out one more thing. The cloud itself is liquid alcohol. And that's the thing you can see. So these lines, the additional lines in this fog, these are, they appear when a particle passes through the fog. The particle interacts with the alcohol and makes a cloud look denser where the particle passed. And even more gaseous alcohol is transformed into liquid droplets of alcohol where the particle passed.
Nice. And it makes such a nice image, but oh, this is so cool. This is so cool. Oh, thank you so much. I will stare at this for the rest of the day.
That's cool. So yeah, science is really beautiful. Well, Anja, do you need any more help with me?
I mean, you can join me in staring in this, but otherwise, I think you probably have better things to do. So, thank you so much. You've done so much for me, and thank you to your co-workers as well, right?
Yes, I will say thank you to my co-workers in your name.
Thank you.
So then I will leave you to explore the secrets of particle physics, some more, and dedicate the remaining time to my co-workers. They surely have some questions. So have a nice day, dear Anja.
Perfect. Thank you. Bye.
Goodbye. So, that was quite a challenge for your first day at work. I hope this was not too overwhelming for you. Thank you for joining our show today. Now is the time for any questions you might have, my dear coworkers. So, my dear audience, you can write the questions in the chat or raise your hand and I will be happy to answer your questions. There is a first question can we make plasma at home? That's a really good question. So the easiest way to make plasma at home is either using a light like a fluorescent tube. If you have them at home already, you are already making plasma at home. Or if you have a plasma ball at home, then that's also an easy way to make and observe own plasma at home. Thank you very much also to Hannah, who wrote thank you so much in the question and answers. Yes, thank you very much for another really positive feedback. Are there any more questions? Okay, more positive feedback. Thank you very much. In the meanwhile, I will make some advertisement in the chat for our website. So if you are interested in the experiments that we have shown you today in our show, and maybe you are even interested in building your own cloud chamber at home, then please check out the following link, cern.ch/school. And yes, there is no H because it's a pun. So on this website, you will find in English many descriptions of experiments about the different phases of matter under the rubric called classroom activities. So please check it out and have some experimental fun at home. Are there any more questions? Okay, since there are no more questions, thank you very much for joining our science show today. I hope you have enjoyed it, and yes, please check out our website if you are interested in further details. And then the remaining thing for me to do is saying goodbye to you, and also thank you very much to my colleagues and to the organizers of the Fantastic Science Festival. Thank you.
Thank you. Thank you so much, Sarah and Anya. It's been an absolute pleasure to watch. I really, really enjoyed it. Thank you so much.
Yes, thank you very much as well. And I hope to maybe see you one day at CERN.
Absolutely. I definitely am looking for an invitation.
That's good. That's good.
Thank you.
Thank you. Then goodbye to everyone.
Thank
Goodbye.
you. Goodbye.